You're terrible. Shall we start? So inshallah today I will be continue as far as I can go. I'm not feeling well. So I will push it as much as we can till, and then I will stop. But I will not go beyond 12. So inshallah, let's try to do the max. So before I proceed, um, let me go back to what we were doing yesterday. Yesterday, I was mostly talking about contraction. Yes? Um, the problem is a lot of people who are working in fixed point theory, they spend their life on contraction. Okay? And if you remember yesterday, the discussion about Piaget and Ziad about D-metric spaces and G-metric, I told you that the mistake was that when you spend your career in one tiny area of the theory, then you don't see the big picture. You're really very... And the problem, really the problem, like the case with Ziad, he has papers that are highly cited. And why they were highly cited? Because at that time, the people could publish. But the moment the people stop publishing in the area, then that's it, it's done. And it's very hard later on to come back and start something. So when you're learning about fixed point theory, especially metric fixed point theory, you may want to have the big picture. If you don't have the big picture, then there is a problem. And I always tell people, always, that people stays between 1922 and 1965. Okay? All their career is between 1922 and 1965. What happened after 1965? Very complicated. The people don't touch it. They like contractions. And different types of contractions. Because it's easier. You have the iterate, it converge. There's nothing. So today, inshallah, I will touch on 1965. I will finish first 1922 to 1965, touch on 1965, move on. But the bulk, and the beauty of what happened after will come, inshallah, tomorrow. Okay? Tomorrow I will show you that. Now, where were we? Of course, there is a lot. I cannot spend, I'll be honest with you, even 5 days talking about 1922, 1965. Too big to be done. So what I did, I chose some parts of the fixed point theory that somehow has some parts that have some interest to us, just interest. So we talked about Banach contraction principle, and we talked about Karisty's idea, and we talked about variation principle, and how I didn't talk about Echelon variation principle. What I did is to connect the Echelon variation principle with Karisty fixed point theory. Okay, so I connected the two. So let me finish by looking at James' advisor, Art Kirk, who asked if this is true, the problem there. The original problem asked by Kirk is the one that you see there. What if I replace the distance from x to tx by the square? Okay? What happens? Okay, so first let us try to understand. I spent a lot of time on this problem. So first of all, what's gonna be a problem? So we have before, we have without the 2, d of x tx less than. That's carries t, yeah? Huh? So now we have a square. And what is the problem? So in order for you to grasp it and to understand it, you need to go to Bronsted order. Okay? You have to. If you don't go to Bronsted order, you will not see the inner working of these problems. Okay? Bronsted helps you, and I showed you how the minimal element of the Bronsted order helped us connect Caristi and Eklund. Okay? So it's a beautiful tool that helps you get a profound understanding of the problem. So now, what happened to my Bronsted order? So we have x less than y, x less than y. I want you to extrapolate, read it in your mind. Okay? So what does that mean, x less than y? X less than y, if the distance from x to y squared is less or equal than phi of x minus phi of y. Yes? Or phi of y less than phi of x. I always have this problem between, do I put phi of x minus phi of y or phi of y minus phi of x? Is the reflection of one order, one relation. So the minimal becomes maximal and maximal. So it's not really a problem. Anyway, so what's the problem then? Okay, choose one and start working. What is the problem with the 2? The problem is that the function t squared is not additive. So you will not have transitivity. You will have what? Reflexivity. It will be a reflexive relation. Anti-symmetric, no problem. But it will not be transitive, meaning x less than y, y less than z, x less than z. And therefore is not a partial order. And if it's not a partial order, you cannot use Zorn-Lemma, minimal elements, and all this stuff. You understand? So the problem is the lack of additivity. Okay? Nothing more. So this is false. This question, this counterexample, I found it quickly, in fact. It wasn't like... so it's artificial. So the answer is no. Okay? So we knew. Of course, I'm talking about this has happened in the late 80s when I got interested into this. So the question becomes now evolved from the original question with the square to this one. Okay? So I asked this question. So the square was R's question. And then I said, okay, fine. This failed. Okay, what kind of function we can put in and have validity of the conclusion? Of course, if eta is what? Additive, then the problem becomes obvious. So the issue is not about additivity, except if you prove to me that the only way you can get a positive conclusion if eta is additive. So remember again, it's very important. Why are we interested in the additivity of eta? It's because of this relation. Do you see it? So as I said here, if eta is subadditive, then this will define a partial order. And therefore, I can use what? I can use the arguments, techniques we developed for charisma. Is that clear? So the question now is, what happens if eta is not additive? If eta is not additive, let me give you a secret. If eta is not additive, what you have here is a relation. In fact, is a graph. X is connected to Y if and only if you have that inequality. So we are getting what? What's called oriented graph. So graphs are an extension of partial order. Okay? Graphs are an extension of partial order. Not any graph, but oriented graph. In other words, there is an edge between x and y if x and y are comparable. Okay? So you put a direction if x is less than y. Okay? You go from the small to the larger one. You put the arrow. Huh? So it becomes an oriented graph. So this happened when my plane was landing in Jeddah. Okay? I was in the plane coming from New York, and I noticed this. So now I saw the connection with graphs. So partial orders are gone. Now I'm working with what? With graphs. So the question is, what is the analog to a minimal element? Now, you have to understand, why am I interested into the minimal? For the reason I mentioned yesterday, that T of x will be less than x, and therefore, if I have the concept of minimal in this context, that T of x must be equal to x, and therefore, x is a fixed point. You understand now? So, the problem is, we cannot talk about minimal for a graph. Yeah? So when I landed King Abdulaziz University, and I asked them, is there anybody in graph theory? Okay? The answer was quick, none. I wasn't staying at King Abdulaziz University in Jeddah. I was going to King Fahd University. Okay? So I flew to King Fahd University, and I asked, is there somebody who works on graphs? And they told me yes. So Munzir, he was a wonderful mathematician who did his PhD in graph theory in a wonderful school in Michigan. So I went to see him. It's very important, this point I want to insist on it. You will see why. And I was told he's no longer practicing as a professor. Now he's in the administration, okay? Taking care of student affairs. I said, okay, fine. I have only one question to ask. So I went to the Dean of Student Affairs office. He was Associate Dean. And they waited. He told me yes. I said I wanted to meet Dr. Munzir. I'm in maths, and I want to ask him something. Okay, after a while. He was busy with students, so after a while, I went inside. And I explained to him my problem, the one that you see right there. So he looked at me in a polite way, and he said, Dr. Amin, I'm really sorry, but my mind has been disconnected from mathematics, and it's just so much on student affairs, student problems. It's hard for me to focus on your question. Okay, fine. No worries. This question went unnoticed for 3 years. 3 years. And then, which I will be touching today on, Mundar is no longer associate dean, is back to the math department. And when I heard that he's back to the math, I went back. So, hey, how are you? So what I did, I went again to see him. And they said, Mundar, to my question, okay? I have this graph, I have this relation, it defines a graph, and I'm looking for the concept of a minimum. What is the analog to a minimum for? Now, I wanted to understand, and Izhar knows what I'm talking about. This was the beginning of an amazing relationship that now, in the world, connecting graph theory with fixed point theory is Monotone. Imagine for a second if I did not insist on asking this question. Wallahi, it was exactly what you see there. This question, I kept hammering it. After 3 years, I wanted absolutely to see what's going on. And just for your information, analog to minimum is the root in graph theory. They call them roots. But anyway, the point is the authority now in the world for bridging graph theory with fixed point theory is Monotone. Amazing what he was able to do. We did some work together, but that wasn't the point. I wasn't interested. I just helped him develop that bridge. So my point is, some of you did not attend my first talk, is sometimes it takes time. It's not fast food. It's not TikTok mentality. It's not like, oh, here's a question from my advisor. I need the answer this week. Or I need the answer by next week. It doesn't work like that. It really does not work like that. Sometimes you have to quit, come back. Quit, come back. Sometimes it takes years before you can see the things fall together. Do you see my point? Or I'm bothering you? I'm bothering you. Okay, I'll move on. I'm going to move on. Okay, so what did they say? Eta is not what? Additive. Okay? If eta is not additive, this is no longer a partial order. It is a relation. Okay? Great. So, something very interesting happened. Truly amazing happened. And I want to share it with you. Now, what happened if, remember the idea of the level of energy? Do you remember? Yes? What happened if we take the infimum? Huh? Remember, phi is always has a lower bound. Yes? Huh? And therefore, we have an infimum. Because we are assuming we are bounded below, and therefore we can assume it's positive. And you have the infimum. Huh? Great. If you have the infimum, think in terms of what I told you, the energy level. Okay? So if you are at closer to the infimum, to the lowest energy level, closer, you are going to find the particles there. That's the definition of the infimum, yes? Take the infimum plus epsilon. You will find an x such that phi of x is less than infimum plus epsilon, bigger than the infimum. Yes or no? Okay. What happens if now I take T of x? Now, what did I tell you yesterday? Which is still valid, by the way. What happened is that T of x will have its excited particle, but the level of energy at T of x is less than the one at x. Yes or no? Because this is positive. This is positive. Therefore, this is less than this. Yes? So when I put T of x, phi of T of x will be less than phi of x. Therefore, if phi of x is less than the infimum plus epsilon, phi of T of x will be also less than the infimum plus epsilon. What does it mean? It means there is an area, certain level, where it's T invariant. If x belongs there, T of x stays there. Do you see it now? And why is that? Why is it that important? Because if it is x and T of x are there, what happens to T of x minus T of tx? So now, the numbers are between what? Between infimum plus epsilon. Yes? But so when you take the difference between them, if you are in that set, what is the difference between the two of them? It's going to be less than this minus this. Yes? This minus this is equal to what? Oh. So phi of x minus phi of tx is less than epsilon. Are you with me? So, see, it can be any number what? Positive. So, remember, I'm working on m. Let's call it m sub epsilon. M sub, this m, call it m sub epsilon. So what is m sub epsilon? Is the set of x such that phi of x is less than the infimum plus epsilon. Are we in? What happened to that m epsilon? It's invariant by t. T of m epsilon stays in m epsilon. Therefore, I am not looking at t over the entire metric space. I'm in a certain region where I squeeze my particles close to the lowest level of energy. You understand now where I'm going? What do I know about phi? What is special about phi? Is lower, so my continuous. Guess what? If it is lower, so my continuous phi, the m epsilon is closed. So if xn converges to x, or xn converges to omega, phi of omega will be less than lim inf of phi of xn. Since the phi of xs are all less than the infimum plus epsilon, the other limit, phi of omega, will be less than the infimum plus epsilon. So it is closed. Since m epsilon is closed and m is what? Complete, m epsilon will be what? Now, let us translate the problem differently. Pay attention. Same problem, but I am not in the entire space. I am in a region where phi of x minus phi of tx stays less than what? Good job. And epsilon, I can choose it what? As close as I want to what? 0. Not equal to 0, but as close as I want. So now look at this now. So it gives me an idea of what's happening in the next slide. Wallahi, is exactly how I took it. What I'm telling you is exactly what happened, step by step. So, now, this we said what? In that region, this will be less than what? All this. Epsilon. Therefore, this one will be less than what? Epsilon. So now I have a function, eta, of some numbers less than epsilon. What I want is this will force what's inside to be linear somehow. Phi will be small. Yeah? Phi will be small. I want the inside, the variable, to be linear. Okay? How do we get that? We get that if the derivative of eta is what? At 0, not equal to 0. Okay? So remember, by the way, I forgot to mention, eta of 0 is 0. Because it's from the condition there. Take x equal y. If you take x equal y, you will get what? Phi of x minus phi of x 0, 0. Eta of 0 will be equal to 0. So eta of 0 is equal to 0. And what I want is the derivative not to be equal to 0. If the derivative is not equal to 0, what happens? Close to 0, my eta of t is just a number which is the slope time t. And therefore, what do I have now if epsilon is very small? What do I have here? I have a number, the slope, 0, time, distance. I am back to what? To Bronsted. So it's not a partial order everywhere. It is a partial order n m epsilon. In m epsilon, I have a minimum. Do you see it now, the proof how? It's not a partial order everywhere. I can squeeze it, stay in that m epsilon, and there I will find what? A minimal element. These are the ingredients why this was done. Okay? So I defined what is what? The minimum for minimal for that relation. Okay? Which is, as I told you, the roots for the graph. Okay? And what you see here is exactly what I just told you. The derivative is positive because the function eta is increased. Okay, let's go to the original problem of Kirk. What was it? What was eta? The square. And what is the derivative of t squared? And what is the value at 0? You see it now? What did we say? It works for what type of function zeta? Additive, yes? So what happened to additive functions? Now you have this identity. See it? So it is also true the condition is valid for additive mapping. So it fails for t squared, but it is valid for additive functions. Now, do we have an example where the derivative is not equal to 0 at 0, and it's not additive? That's the one you see on the screen. Okay? The derivative is equal to 1 at 0, and this function is not. Now, of course, once we did this, or once I published this, people did what? To improve on the derivative not equal to 0. Okay, so there is work that was done after this. I didn't want to bother you with this. It's just to give you a feeling of some of the problems and how it impacted the research a little bit with some patience. Okay. Second. Okay. Now, I want to talk about something different. Okay? And something that is impacted fixed point theory for years, but it came late. Okay, it didn't come at the same time as 1922, 1965. Okay, it's fairly recent, and it's attracted big attention, big attention. So I want to touch on it, and then I will explain to you why our friend Mondor is considered now as being the leader in bridging the graph and fixed point theory. So in order to start, let us go to what is a monotone mapping, okay, or increasing mapping. So you have partial order, and you have t that satisfies x less than y, t of x is less than t of y. Okay, monotone mapping. Okay? Now, when we talk about monotone mapping, what comes to mind is Tarski's fixed point theorem. Okay, so it says if the order is good, then any monotone map will have a fixed point. In fact, there is more to the story. Okay, this is old, by the way. This is very old. So you have Tarski, 1955, and you have Knaster and Tarski. Tarski was doing his PhD with Knaster. Knaster, 1928. This is typical. Okay, that at that time, somebody will be working with someone, like, for example, injective matrix spaces, Shpaqli and the Rangen. Advisor has some ideas, and the student will start working on it 30 years later. So don't be surprised if you see a gap of 20, 30 years in between them at that time. So this is common. So this theorem says what? That if you have a nice order, what's known as complete lattice, and you have T which is monotone, okay, increasing, then T has a fixed point. Okay? T has a fixed point. In fact, more than that. The set of fixed points of T is what's known as a sublattice. Okay? Powerful tool. If you remember, I told you this is the beginning of what's known as discrete fixed point theory. Discrete fixed point theory. Great. Known, I mean, we know of this. Now, 2002. So, 2002 is Dutch, from Dutch land. And the Sayyid is Egyptian, and he was visiting Rand, doing research with him. Okay? And they looked numerical approximations, numerical work, numerical mathematics. They were really doing some heavy computational work, okay? And they were looking at this matrix equation, okay? So, want you, from yesterday, to tell me about this equation. Yalla. Tell me about it. Wallahi, I didn't hear you. What is it? Fixed point equation. Why I'm asking you? Moving forward, every time you have this, oh, this is a fixed point equation. I may use what? Fixed point theorems, or maybe some techniques. Do you understand now? Many people don't see this. So this is a fixed point equation. But when they did it, they didn't treat it as a fixed point equation. They worked on it using like properties of Hermitian matrices, and they were able to prove that this equation has only one solution. And one way to find it, if you take the right-hand side as an operator and you iterate it. So let me repeat myself. Okay? This equation has only one solution, x. Okay? One matrix. Number one. Number two, the way they prove this, you take the right-hand side. This right-hand side is like an operator. T of x. And if you iterate T of x, the iteration sequences will converge to the solution of this equation. Okay? So, huh? Yeah, I mean, these are expensive. Yes? There is only one tiny problem. It's not a contraction. So, the conclusion, I lied, tells me there is maybe Banach contraction. But when they checked, that operator on the far right is not a contraction. It didn't fly. They did it, but it didn't fly. I didn't care because from a numerical point of view, they needed the solution. So it wasn't like important to develop a theory behind it. You understand? It wasn't their goal. Their goal was to find the solution. That's what they wanted to work with the solution. Years later, Röhrings, she's a student who came to do her PhD with Rand. Okay? And Sayed was around. So they started working on this equation, but this time a little bit more complicated. Okay? Not that much. Which is now, instead of having one matrix AFX, or A star F of XA, you have now family of what? Matrices. Okay? So, she looked at this, and what she found out that, in fact, this operator on the right, okay, what happened to it? If you take at 0, x equals 0, okay, what happens? You will get Q, because f of 0 is 0. Okay? So, that is the image of 0. Okay? And now you take the image of Q. Why am I doing this? Huh? Exactly. Okay. Now what they noticed is this operator, like before, was not a contraction. But if you put the right assumption on Q, what happened to this is that there is an order between the matrices. And if the matrices X, that operator is a contraction. This is new, totally new. So now, let's go back to Banach. What does Banach say? For any x, any y, the distance from tx to ty is less than constant time the distance from x to y, which is condition. Yes? Here, no. You have it, but not for any x and y matrices. Only for matrices that are comparable. There is an order, and if two elements are comparable, T of x and T of y, we have this contraction idea. Number one, that operator is monotone. So, of contraction on comparable elements. Are we in? Okay. So, later on, I discovered that Turinisi, who was a famous mathematician, really a beautiful guy, did work on this. But He was in Romania and was not widely known. So these people from Holland did not know about this. I know this. Okay? So here we are. Of course, and Rönings did not know about this definition. This came afterwards. But they had it in their paper. Okay? They were looking at it from a numerical point of view. Okay? So if we formalize it, what do we have? We have M, which is a metric space, with the partial order. So you see, you have M, D, partial order. Okay? M, D, partial order. T is what? Monotone for what? For the partial order. And for comparable elements, that's what you see there. For comparable elements, if X is comparable to Y, X and Y, you have this condition. So we call them Lipschitz monotone mapping. Lipschitz monotone mapping. If the constant K is less than 1, then they are called monotone contractions. Are we in? So far, so good? Yes? Like R. R is the most beautiful example where you have the order and you have the distance, the absolute value. Now, assume you have a fixed point. Focus on the contraction. For non-expansive, I will talk about it later, after I'm done with 65. Focus on monotone contraction. Okay? So the goal, and that's what they did, Rand and Rönings, as well as Sayed and Rand, they want to prove the existence of a solution. Therefore, a fixed point, yes? So you want T of X equal what? X. If X and T of X, if X exists, we know by reflexivity of the order that X and T of X are comparable. Do you agree? So if I know that no X is comparable to T of X, there is no way we can find a fixed point. Do we agree on this? Okay? So remember, the partial order we have reflexivity, anti-symmetry, and transitivity. Yes? So if you want a fixed point, T of X equal X, you must have at least an element X such that X and T of X are comparable. Otherwise, it's not going to work. The reason why I'm telling you this, we visited Mian Mondor, a Chinese mathematician who got the medal, field medal. And we visited him in Harvard. And we were talking in his seminar. His name is Yao. In his seminar, and his question was, why are you assuming there is an X such that X and T of X are comparable? Why am I telling you this? Even the best among us sometimes don't see the small stuff. That are obvious, but they don't see it. This question, I heard it so many times. Why are you assuming X and T of X are comparable somewhere at certain point? But the reason is one I told you right now. Okay? There is no other reason. Because the problem is to find it. Okay? So now, let's take X0 comparable to T of X0. So now I need your attention. Follow me now. I'm going to focus on what? Contraction. This one I will talk about it later. So take X0 such that X0 and T of X0 are comparable. Once I know they are comparable, I can use the contraction on them. Yes or no? Because x and y are comparable. So what is the image of x0? They have x0 and t of x0. What is the image of x0? T of x0. And what is the image of t of x0? T squared of x0. Do you see where I'm going now? So x0 is comparable to t of x0. And what do we know about t? Monotone. Therefore, t of x0, t of x0 squared will be what? Comparable. Yes or no? And then another t, another t, another t. So what kind of points I'm dealing with? Remember, from yesterday, come on. So I'm looking at the iteration. And all the points generated by the iterations are comparable. If they are all comparable, I can apply what? The contraction condition to them. That was the condition what? In Sayed and Ran and Roering. To make sure that 1x0 is comparable to what? To t of x0. That was the technical condition they put on their theorem. Okay? Now, so you have this orbit, Tn of x0, and they're all comparable, and they satisfy what? Tn, huh? With power n. So let me show it to you now. It's the same as what? As Banach. As Banach contraction. So now, follow me now. I wanted to do this before you see it, okay? So you grasp it better. So now we have x0 such that what? x0 is comparable to t of x0. It doesn't matter, by the way, which one is bigger. One sequence will be increasing, one sequence will be what? Decreasing. So it's not really. They're comparable. Then what do we have? We have the comparability of what? Of the orbit, yes? And then I can use the contraction because they are comparable. And what you have here is k to the power n. Because of k to the power n, and this is a number, same triangle inequality will tell me that this sequence is what? Is Cauchy. And therefore, if it is Cauchy, it converges. So far, this is all valid. So what do I want to say afterwards? I want to say that the limit is what? Is the fixed point. Number one, you need some assumption of t. T monotone and monotone contraction doesn't have to be continuous. So the limit may not be what? In the case of Ran and Roering, it happened. In their case, it worked. And that's how they explained the solution to their problem. Now, so what's the question is? Fine. We have a limit. Huh? Omega exists. In general, omega is not what? Fixed point. Under what condition for omega to be a fixed point? Number one. Number two, omega depends on what? On t and x0. In the case of Banach, what happened? We have, because of the contraction, you cannot have more than what? One fixed point. And therefore, the fixed point is independent of what? Of the initial point. Here, how do I connect? If I take x and y, how do I connect the two? To connect their orbits. You can't. You can only connect if x and y are So if they are comparable, the limit will be the same. Yeah. Tn of x, Tn of y, the distance will go to 0 for the limit of Tn of x, and the limit of Tn of y will be the same. But what happens if x and y are not comparable? So you see, it's a version. Okay. So what are after run and rurings, everything was smooth. It was really nice. Then you had some people in Poland where they looked at this problem and they started looking at what conditions on the partial order for which that limit is a fixed. So you have papers that were published. Oh, no. First one. T is what? Continuous. T is continuous on M. Then you have a fixed point. No doubt. Omega will be a fixed point. What about if T is continuous on the orbit? Because I don't care about having continuity of x and y close. T of x and T of y are close. Only focus one on x and y, which are what? You see, it's like comparable. Because we have good behavior on comparable elements. And that's why we want to be only on ask me to give an example on a map that is continuous on orbit. I have absolutely no idea how to find one. But it's published. That one was satisfied that if you have an increasing sequence with a limit, the limit is bigger than order. In fact, it's the supremum. Be careful. We are not in R. Don't look at it as R. It's obvious in R, but we are dealing with space with a partial order. That's not R. There is no reason for this to be true. So you have a sequence which is increasing with the limit. Limit for what? For the distance. Combining now the distance with the topology with the partial order. Are you with me now? So if you have that condition, and that was seen by people, and drawing, then omega is a fixed point. Ready? It's not complicated. About the T of x. Yeah? The case of x less than T of x. Or the C. So what do we know about it? It's going to be the supremum. Yes? Therefore, omega is comparable to all of them. So what happened to T of omega? It's going to be bigger than T n plus 1 of omega. Then T of omega becomes an upper bound. Therefore, T of omega is going to be bigger than what? Than omega. Next, you show that omega is bigger than T of omega. And that's how you get what? T of omega equal omega. Okay? Now, so these are what? The assumptions. And you have omega being what? Fixed point. The two. It is. Now, let's unicity. Okay? The uniqueness of the fixed point. when do we have the uniqueness of the fixed point? We have x0 and we have the orbit of x0, Tn of x0. It converges to omega, fixed point. Let's take x, which is comparable to x0. Okay? Then Tn of x and Tn of x0 will go to 0. The distance will go to 0. Since this one goes to omega, this one will go to omega. Okay? Now, what if you have 2 points, x0 and x? They are not comparable. What if you have y, which is comparable to both of them? So, Tn of y, Tn of x0 goes to 0. Tn of y, Tn of x goes to 0. Therefore, Tn of x will converge to omega. So, if you have, for any two elements, an upper bound or lower bound, you are okay. Now, I want to show you something here. Now, a little bit far. Let's R2. And what you have to understand is, I just said partial order. Partial order can be as artificial as you want. Define one. You have a partial order. And you assemble on the partial order. X, Y, so Y. Let me do it here. Y equal X. I'm looking at this. Okay? Go. Yes? This set, no, partial order, which is what? If A and B less than 1. It means this point and this point, this one is bigger than this one. Are you with me? You take this point and any point anywhere, they are not comparable. Okay? So, let's look at now increasing sequence. Now you are going to get something interesting. Let's take sequence of points which are increasing. So if they are increasing, they must be in one. Yes or no? Yes? What distance I am taking? Euclidean distance. So increasing sequence, segment, this segment is compact. Therefore, my sequence will have convergence. The whole region is not bounded. It's not what? Compact. So this example was that under this technique, monotone repetition mapping, there is more than what they were doing. So there is something called order topology. This is just an example. And by the way, we came up, I will be talking about this, of something called order uniform convexity. Order uniform convexity. So let's move on. There is to this story that we don't know. Okay. Now, this is our first paper in this area. First, on this model. So what I was interested in, so it was and okay, looking at chemistry. So look at the definition. It's very interaction, how it was done, and therefore we have x comparable to T of x, and you have now. Okay, so our result was about this type under this condition. Okay. I want to show you the condition that if you have a sequence that is decreasing, the limit is the infimum, because in the other one, it's just bigger. That was Jashinsky and others. It wasn't equal to the supremum or the infimum. Okay? So this condition, for the case of Caristi, tells me what? That if you have that OAC property, then you have a fixed point, provided you have an element x0 such that T of x0 and x0 are comparable. And you understand now why this condition. When you see a paper published in this direction, you understand. If they don't, there is no way you will have a fixed point, period. Seven. Okay? Jashinsky, what he did, the partial orders, they define naturally a graph. But graphs may not be partial order. So he took Ran and Röring and he gave a graph formulation of that one. That's the paper that you see there. And when you have a sequence that is increasing, you just replace it by what? By a graph definition, meaning what? X less than y. If you have a vertex going, is a directed graph. You need to have a direction, oriented graph. So x going to y, that's what it means. X less than y means x going to y. And therefore you have this path, x1, x2, x3, and you have the path going. And you assume what? That you have an element that is basically bigger than all of them. So he put it similar to the partial order. But what I wanted to understand is this. So in his original paper, assumed that for the graph, the vertices is the entire matrix space. Okay? It's a matrix space. Therefore, between two vertices, may have, look at this example. So if you take this point and this point here, there is no edge between them. But between this one and this one, we have an edge. Okay? We don't have an edge, and we have what? The distance. Because we are in a metric space. So run and put it in terms of what? We got involved. So what does this mean, monotone? This means that if there is an edge between x and y, there is an edge between tx and ty. So you have what's known as G monotone. And what does it mean to be a G contraction? If you have a constant case such that this is happening whenever you have an edge between x and y. Okay? Remember that we always assume that all the edges, all the vertices, is the entire metric space. Okay. So you have this property. Look at this property. It's very interesting. xn plus 1, you have an edge. Yes? It's oriented. So it's like xn less than xn plus 1. That's what it means. So the limit, if there is a limit, is going to be bigger than them. Yes? So if it is bigger than them, it means I have to put it where? I have to put it to the right. Yes? That's what you see here. Okay? Of course, I don't need the entire sequence. I just need a subsequence. And this is just refinement. Whether you want to work with what? Subsequence or a sequence makes no difference. Okay? But this is exactly the condition I showed you before. And it was done in terms of what? Graph. And now you have this theorem again. Okay? The graphical formulation of the RAN and the rings. This is the main result of the paper by Jashinsky. Okay. This is very important to explain to you because I wanted to touch on this, especially the flower shop, if you remember. As the distance from B to A. Do you remember this discussion yesterday about the flower shop? Since I wanted to buy some flowers for my wife? Yes? Did you wonder why? I'm not talking about buying flowers to my wife. I'm talking about why the distance from A to B is different from the distance from B to A. Did you wonder why? Huh? It's because the roads, when we drive, we don't drive in Euclidean space. The distance between this point and this point is exactly the same as the distance from this point to this point. You understand? This is valid. The problem when we are driving on an oriented graph. And therefore, we are going on the graph from A to B. There is no reason to follow the same what? Path going from B to A. Therefore, the distance will not be what? Same. This graph, the road, that is the basis for your GPS, in fact has a technical name. And I did not know that. It's known as a weighted graph. So what do you do now? You have vertices, you have edges, And to every edge, you associate a weight. In the case of the GPS, is the distance of the connection that you have between this vertex and this vertex. Are you with me now? So what did we do? We took the theorem of Jashinsky and everybody else, and we told them, in fact, we are not on a metric space. We are on a weighted graph. And this is part of what's known as analysis on graphs. They are doing a lot of work in this direction. So we started now to work or push in this direction. Okay? Let's go back to Kirk yesterday. What did he ask James? He asked him to find what? I'm just testing whether you are with me or you are not with me. I spent a very bad night yesterday. Very bad night. That's why you see I don't have that much energy. Right? So what was the question from Art, Kirk, to James? I love you guys. Wallahi, I love you. I wish my students were like you. So that question opened the door to definitely what? You remember, I told you a window that we discovered crazy things with charisma. Crazy things. And in fact, thanks to charisma, that Eklund was able to discover his variation principle. It's crazy. It's crazy. So my point is, sometimes either you stick to the obvious or you push it a little bit more. So the idea of a metric space with a partial order, a metric space with a graph, we find everywhere. But wait. We don't need a metric space. We just need to work on the graph. And it's known as a weighted graph. Okay? But the people who are working on weighted graphs, they never connected what? To a fixed point problem for monotone mappings according to the graph. Do you see where we are heading with this? Huh? So of course I didn't want to teach you what they do. There is a book written by Monotone. So I didn't want to tell you more about what's going on, but I wanted just to show you how if you push it, if you keep pushing it, you may find something interesting. Again, how do I push it? You cannot push it by staying what? Artificial. You can't. Or for example, have a paper at the end of the week. You can't. So you need to push it, and sometimes you will get somewhere, sometimes you will get nowhere. But that's part of what? Of the research. Are you with me? Tell me. I'm bothering you, huh? Okay. So, I wanted just to touch this. I don't want to spend a lot of time on this. So, let me now move to 1965. Okay? Real business. So the question was, 1920. Mapping. But he so equal distance xy isometry. So they are non-expansive, but they are not. the unit circle, and take a rotation. Good. Centered so what is the image of this element? Okay, that is going to be this element. How much do we have here? Okay? So we know that rotations are, okay? And what is special about this? Do we have a fixed point? Do we have, do you see a point that is invariant? No. No way. Except, of course, if your theta is multiple to pi, but I'm taking like 30 degrees. Now, let's look at this rotation in the plane, not on the unit what? Circle. In the plane. Okay? You understand what I'm saying, yeah? So, this goes here. This goes here. This goes here. There is one invariant point, which is what? 0, or the center of the rotation. Yeah. So you see, if I look at it in the plane, I have fixed point. But if I look at it on what? On the circle, no fixed point. And it is an isometry. So it is non-expansive. And the circle is compact. Beautiful. Okay? Not only complete, compact. It will not help you. So they knew this. Okay? They knew that, and also what happened if, so this tells you non-expansive, huh? Will not give you a fixed point. What about if I have what they call strict, contractions? Not contractions. In the old days, it wasn't with constant Lipschitz K. What? So this one, you need kind of compact. Because T is compact. If the domain is compact, the minimum between x and T of x, and you're done. So you take what's known as the displacement, minimal displacement. So what is the minimum displacement? So it's inf of the distance x dx, x in x. So they call it the minimal displacement. And what we want is that this minimum will be equal. Well, and we achieve 0 somewhere. In general. Okay? But if you have and be achieving this somewhere, and that somewhere will be a fixed point because of this condition. Do you see it? Huh? Okay. Now, what is the difference between the rotation and the rotation everywhere? Who wants to tell me? Well, I didn't hear you, sorry. No. Of course, it will work if I have strict non-expansive there. It will be nice, yeah. But no. Anybody else? It's very important. What's the difference? Again, my question. Wallahi, I didn't hear you, sorry. rotation has no fixed point. One, the rotation has a fixed point. Your friend was very important. It's inside the circle, yes? So, if I take this, pay attention. Huh? If I take this and this, will it work? Therefore, mass have center. Therefore, I have to assume what on the domain? If you convexity on the domain, we are no longer in metric space. We're talking about 1965, not today. I know what to do in abstract metric space. 1965, they did not know what to do. So for them to go from a metric space to add convexity to it, we go to what? To a vector space. When they start looking, they move to Banach space. No, this was known. And by let me stay with what I'm going to show you. Throughout after 1965. Ready? Let me show you. No, this is just in a Banach space. What it matters, huh? In a Banach becomes what? Huh? The distance becomes the norm. Yes? So this was going on in the 60s and the 50s. Okay? This part is vital. What you see on this slide is vital. It's connected to what I wrote there. Now, look at this. So we have T from K to K, and look at this. Why T epsilon goes from K to K? Why? Yeah. You understand? So we are using domain is convex. Enforced. Let's continue. That is a fixed point. I'm sorry, a fixed point, not in the sense of fixed point theory. It's like a point. Okay? So and they stay with point, which means what? Contraction. Therefore, fixed point. Wait. How point? What? You know that iteration? X epsilon equal to this, yes? Huh? translation, fixed point. Which means what? That this moment is equal to what? The minimum displacement is equal to what? So guess what? From a numerical point of view, if epsilon is 10 to the power minus 100, I reached the fixed point. If epsilon is 10 to the power minus 100, my x epsilon is the x epsilon close enough to t x epsilon up to 10 to the power minus 100. They are the same. Computer. This is profound. Let's take epsilon for 1 over n. So let's call x over n n. We have xn minus t of xn. N to infinity, this goes to where? 0. N minus t of xn goes to where? So this is known as an approximate fixed point sequence. Okay? So, 1960. It will not be complete to use what? Is what do we do with this approximate fixed point? If it's compact, then you have fixed point. You understand? Because the subsequence will converge, the limit will be a fixed point. You understand now? What kind of assembly can put are weaker? Still ensure what? That now 2 or 3 slides, but I will not do it. Browder. Let me show you the paper. But I was not interested to find the fixed point. Trying to solve approximate fixed point sequence. Okay? If who did a paper on fixed point of what? Non-expansive mapping. I'll come back to this tomorrow, inshallah. It's this guy. The paper, I asked the AI assistant, and it says on contractive mapping, but in fact it's not contractive in the sense we know. Contractive on fixed point theory for non-expansive mapping, which means the beginning of